This morning, we're going to be talking a bit about how a typical neuron generates a resting membrane potential. And if we go back in time a little bit, we should recall that there are three primary molecules, ions, that are going to help to generate the resting membrane potential. Sodium ions, which I've indicated in red, these little guys, Na+, potassium ions, K+, and large negatively charged proteins, or anionic proteins, as these great big A minuses. Now, you'll notice that as we get started, we've got in blue, I'm going to say, our typical neuron, and in white is the extracellular space, the space outside the neuron. And we notice we've got a pretty even distribution of sodium and potassium on either side of the membrane of this typical neuron. There are large negatively charged proteins trapped inside the cell. They can't get out. They're stuck in there. But we remember back to some of our molecular movement tricks, and we realize, you know what, I can move sodium and potassium ions across the membrane if I've got the right tools. In the case of your typical neuron, these tools that are going to allow me to move sodium and potassium ions across the membrane relatively easily are the sodium potassium ATPase pump. This is that molecule. It's a carrier protein that uses ATP energy to actively use energy to move sodium out of the cell and potassium into the cell. Potassium leak channels. So basically, these are holes in the membrane that allow potassium to just leak through, and sodium leak channels. Another thing we notice is I kind of drew the potassium leak channel considerably larger than the sodium leak channel. You know what? If I've got a bigger hole, it's going to be leakier, and what we're going to see is that more potassium is going to diffuse across the membrane passively than sodium is, because the leak channel for potassium is leakier. So I think the easiest thing to do is just to throw everything on the wall and see what starts to happen. So if you went through and counted all the pluses and minuses on either side of the membrane right now, you'd see that you get something like 16 sodiums and potassiums outside, 19 sodiums and potassiums inside, and then 3 A minuses inside. So if I add all the pluses and minuses, there's no difference in charge on the inside or the outside of the membrane. There's the exact same electrical charge. Now I'm going to turn on the sodium potassium pump. I turned it on, and boom! And boom! Let's try one more thing. And boom! There we go. And boom! The sodium potassium pump just pumped 3 sodiums out and 2 potassiums in. And every time it uses an ATP, that's the ratio of sodium out to potassium in. If we do it again, 3 more sodiums out, 3 potassiums in. And now we start to see that we're generating a difference in sodium and potassium distribution across this cell membrane. And we know that things want to move, well, from regions of high concentration to low concentration. And since there's more potassium inside the cell now than there is outside the cell, potassium's going to want to diffuse out. There's some potassium goes out. And sodium's going to want to diffuse in. There goes some sodium in. But more potassium is going to diffuse out than sodium is going to be able to diffuse in. You know, I'm going to run the sodium potassium pump one more time. 3 sodiums out, 2 potassiums in. And we've gotten to this place where just through a few rounds of letting the sodium potassium pump go with the potassium leak channels and the sodium leak channels in place, where I've got a really different situation than what I started with. I have, relatively speaking, a high concentration of sodium outside the cell and a high concentration of potassium inside the cell. If I start to add up the pluses and minuses as well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I've got 21 positive charges outside, no negative charges, and now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 positive charges inside, and 3 negatives, kind of sort of for a net of, what would that be, plus 12? Or another way I can think of it, if the outside's plus 21 and the inside is plus 12, you know what, if I say the outside's 0, the inside would be minus 9, or we can leave it at the inside is more negatively charged than the outside is. So we set up a situation where we've got 3 gradients going on right now. There's a potassium concentration gradient because we've been pumping potassium into the cell, and that concentration gradient wants potassium to diffuse out. I've got this arrow in green. There's a sodium concentration gradient that wants sodium to diffuse in. I've got that arrow in green. We've also got active transport that's actively pumping potassium in and sodium out. But we've also generated this electrical gradient. These big negatively charged proteins that are trapped inside the cell make sure that the inside of the cell is more negative than the outside of the cell is. Both potassium and sodium are positively charged ions, which means, well, if they're positively charged, they're going to be attracted to negative charges and be repelled from other positive charges. So if it's more positive outside and negative inside the cell, the electrical gradient for sodium wants it to go into the cell. The electrical gradient for potassium wants it to go into the cell. And when we turn on that sodium-potassium pump with the potassium leak channels and the sodium leak channels, eventually we get to these equilibriums where the concentration gradient of potassium diffusing out because of those great big potassium leak channels is exactly matched by the electrical gradient and active transport moving potassium in. Same thing goes for sodium. The active transport of sodium out is going to be matched by the concentration and electrical gradient of pushing sodium back in, and we wind up with an equilibrium where it's more negative inside the cell, more positive outside the cell. Oops. But let's call that for a day.